So this is Professor Lars Hesselholt, and I'm delighted to introduce him. So Lars is, of course, a pioneer and leader in the application of trace methods to algebraic K-theory, interpreted very broadly, and delivered an address to the ICM in 2002 on the subject. I first met Lars when he was in Aarhus, and from there he got his PhD in 1994 under Madsen, a connection which of course has remained close for a long time. After that he moved to MIT, first as Moore instructor, then as associate and assistant, and then as associate professor with tenure. And then in 2009 he moved to Nagoya as a full professor, maintaining, of course, his connections with Denmark in general and Copenhagen in particular. And from 2013 to 18, he had a visiting Niels Bohr professorship in Copenhagen, and I think he spent half the time in each one. And at that point, he developed that's 2018, he developed an interest, a close interest in automotive engineering, because that led his two universities to make it possible for him to hold professorships permanently, both in Nagoya and in Copenhagen. So we may be about to learn the applications of automotive engineering to his topic, so Lars, I'm delighted to introduce you to talk about algebra and arithmetic.
Yeah, thank you very much for the kind words and and for the opportunity to speak here. Maybe we can get rid of this. So, yeah. Yeah, so maybe let me write here. So let me first recall that to a regular geometrically connected scheme, x of finite type over the integers is associated the zeta function. So, which is defined by this Euler product indexed by closed points in x of 1 minus the cardinality of the residue field at x to the minus s inverse. So this sum converges absolutely if the real part of s is greater than the dimension of s, and there are it's conjectured to have a meromorphic extension always. This is known in some cases, and we heard about this a week ago. Now, if x is defined over a finite field, let's just say over fp, then this residue characteristic is necessarily a power of p. And so this implies that the zeta function is periodic with period 2 pi I over log p. Or equivalently, we can write the zeta function as some other function of p to the minus s. So the Grothendieck school developed a cohomological interpretation of this function z, and used that to prove the analogues of the Riemann hypothesis in this situation. Note, however, that the zeta function itself has infinitely many zeros and poles because of this periodicity. If S is a zero, then any multiple of this number plus S is also a zero. So even in this case, the zeta function will always have infinitely many zeros and poles. So if we so the cohomological interpretation, maybe I should say, on the other hand, this function here is a rational function of t, and so this admits a cohomological interpretation by a finite dimensional cohomology theory, but we can never expect to have a cohomological interpretation of this function by a finite dimensional cohomology theory, even if we are over a finite field. In general, we cannot rewrite the zeta function in this way, and therefore we should look for a cohomological interpretation of this function itself. So Denninger has proposed what such a cohomology theory with this property, what that should look like. And what I will try to explain today is that at least in the situation over a finite field, such a cohomology theory comes naturally from taking higher algebra serious. Okay, so the picture that I had up here in the beginning was of this bone from Isanko, which is 20,000 years old, and is the first example of human symbolic writing of any kind. And so obviously people were looking at some finite sets of things and trying to organize this in some way. And what they came up with was to take homotopy groups. So pi naught of the category of finite sets and isomorphisms is the natural numbers. And what we do when we count is we determine which isomorphism class does our finite set belong to. That we always get the same is not a completely trivial theorem. I'm sure that the people 20,000 years ago empirically understood that this is the case, but it's not completely trivial. Then later we added negative numbers, and to get the integers, and studying the integers is where algebra came from. Now, Waldhausen, Waldhausen made some very important contributions to algebraic K-theory, and his basic philosophy was that it was a mistake to take homotopy groups here, that we should work on this level as long as possible, and taking homotopy groups is only something we should do at the end. So the natural numbers is the free monoid on one generator. In the same way, this is the free E-infinity monoid on one generator. And it makes sense to also add negatives here. And if we do that, we get the free E-infinity group on one generator, which is the sphere spectrum of homotopy theory. And when we study that, we are led to higher algebra, which is now much developed thanks to Joyal, and in particular Joyal Lurie, who has done an enormous amount of work in this direction. So it turns out that while it's technically more difficult to work at this level, there are also many advantages. So, for example, the derived category of abelian groups is as a presentable stable infinity category is generated by a single object, namely Z. But it's not freely generated, so there are relations. However, the corresponding category here, which we could call the derived category of the sphere, or which is called the category of spectra, as a presentable stable infinity category is freely generated by the sphere. So this is much easier to work with than this is. So both have a T structure, and the T structure in both cases is abelian groups. And so my argument is that this is the correct generalization of abelian groups, and chain complexes is something very difficult. Okay, so now I will explain. So the cohomology theory, which will give a cohomological interpretation here, is the analog of the Rham cohomology, but with the sphere as the ground ring. So let me first recall how the Rham cohomology works. So first, how do we define differential forms? So let A be a commutative K algebra where K is a commutative ring. So then the Rham complex of A over K is the universal example of a commutative graded ring that receives a map of commutative graded rings from A equipped with a K-linear derivation that is a differential. Okay, so if we consider smooth forms, then smooth differential forms, if we just know the category, if we just know the algebra of smooth functions, then constructing differential forms is just an algebraic process from that. Now, Kohn and Sagan wanted to generalize this to a non-commutative situation, and they made the remark or the observation that having a differential as this one, which increases degree by 1, is the effect on homotopy groups of having a circle action on the thing that you take homotopy groups of. So let me just, very simply, if X is a topological space equipped with a circle action, so T here is the circle, then if I take homology in degree J, then I can cross with the fundamental class of the circle that brings me here. And now I can take the map induced by the action to get here. So the effect of composing these is a differential on the homology groups. And so this is what you see on the level of homology or homotopy from having a circle action. So now in higher algebra we can just do the same thing. So we take A, and now we ask for a commutative K algebra equipped with a circle action through algebra maps together with a map of K algebras from A. And the universal example of such a structure is by definition Hochschild homology. Oops. Okay. Now, on the level of homotopy groups, so here this is the homotopy groups of this spectrum. The circle action induces in this way a differential that increases degrees by 1. But the de Rham complex is the universal example of such a structure. So there's a unique map here from the de Rham complex to the Hochschild homology groups compatible with the differential. And a classical theorem of Hochschild, Costin, and Rosenberg says that this is an isomorphism if A is a smooth K algebra. Okay. So, but let me massage this general definition a little more. So, another way of saying what this is to say that this is the t-fold tensor product of A over K. So if I put a set here, then we would all know what it means to take the x-fold tensor product of A over K. But in higher algebra, sets are replaced by spaces. The role of sets is replaced by spaces, and so this makes perfectly sense. Now we can take the circle and break it in two. So write the circle as two one simplices glued along their boundary. So if we do that here, we have this, and this tensor construction is a left adjoint, and therefore it commutes with co-limits. So this is the same as saying that this is A to the tensor delta 1 tensor over A to the tensor, the boundary of delta 1 A to the tensor delta 1. And delta 1 is contractible, so this is the same as A tensor over A tensor over K, like that. So it's the derived product. So the boundary of delta 1 has 2 points, so this is the twofold tensor of over K, but in the derived sense. And then we further tensor these 2 copies of A in the derived sense over that. So let me calculate this in an example which is not smooth. So what is the Hochschild homology of Fp over Z? Okay, so we should So let's first calculate this. So now A is Fp and K is C. So I should replace Fp by something which is free as a Z module. So I replace it by an exterior algebra on a generator y in degree y with differential p. So these are equivalents. So this tells me that if p derived tensor over C, if p is an exterior algebra on a generator y in degree 1 and now with trivial differential. Okay, so now I have calculated the basis for this tensor product. Now I should replace Fp by something which is free over this differential graded ring. And so this is, take this and tensor with a divided polynomial algebra on a generator in degree 2. So let me write the divided. So this is a polynomial algebra on x squared over 2 so like this. But note that for example x to the p is now, so x to the p is now p factorial times x over p factorial, which is therefore 0. So this is a yeah. Let me also write like this. Okay, and so here the differential on this nth divided power of x is the n minus first divided power times y, and so you can check that this is a resolution. Okay, so now finally to calculate the Hochschild homology of Fp over C, we have to tensor this over this ring with Fp, which just removes that, so we get that this is the divided power algebra on this generator in degree 2. So the fact that you get these n factorial in the denominator here is no coincidence. So this happens for any commutative ring. For any commutative Z algebra or K algebra, for any commutative K, the subalgebra of even elements has a divided power structure. So yeah. However, if we instead do the same thing over the sphere, then these disappear. So instead of getting the divided power algebra, we get the actual polynomial algebra. This is Bökstedt's periodicity theorem. And if I have time, I will explain that this implies Bott periodicity, but is a stronger statement. Yeah. So philosophically, in retrospect, this makes good sense because we have exactly the reason that the n factorial appears here is because that when we define the natural numbers, we identify the n factorial ways of counting to n to the same entity, and we don't do that here, and that's why this denominator disappears. Other places where we see denominators is in the definition of the Chern character, and again we will see it's for the same reason. When we work over the sphere, we can have a multiplicative Chern character without denominators. Okay, so much for differential forms. Now we have to globalize, so we have to sheafify. So if x over k is a scheme, and let me assume that this is smooth just for simplicity, then the Rham cohomology of x over k is defined in such a way that we have the Hodge to the Rham spectral sequence which looks like this. So as A varies through the open subsets, the affine open subsets of X, we get a sheaf or a complex of sheaves, and then we take an injective resolution of that and take the total complex and take cohomology. That's what the Rham cohomology is, and the filtration of this total complex gives this Hodge to the Rham spectral sequence. So it sits here in the first quadrant. If the dimension of x over k is d, it sits in this square, and the total degrees add up in this way. However, now the Rham complex is the homology of this other complex where the differential goes in the opposite direction. So we can sheafify at an earlier stage instead. We can sheafify the Hochschild complex and then take homology of that total complex and call that Hochschild homology. And now the spectral sequence instead will look like this. So we have the same, so the constituents in these groups are the same groups as before, but they are now arranged in a different way. Namely, they sit here. And now the total degrees add up like this. So we get from this picture here to this picture here by rotating 90 degrees. So this edge here is that edge, and this edge is that edge. So this is the A picture, and this is the B picture. And I don't know what this means. This is how mirror symmetry is supposed to work. So the Hochschild homology looks as if it is the Rham cohomology of a mirror dual of X. And so in these theories, we always have this picture. We don't have this picture. Yeah. Maybe I forgot to say one thing about this map here. Namely, we can see that map as the edge homomorphism of a spectral sequence. which begins in the Hochschild homology of Fp over the homotopy groups of the sphere. So these are the stable homotopy groups of spheres, and which converges to the Hochschild homology of Fp over the sphere. So the edge in this spectral sequence where j is equal to 0 is the Hochschild homology of Fp over z, pi naught of z. Pi naught of the sphere is z. And Serre proved in his thesis that all the higher homotopy groups of spheres are finite, and somehow this says that they have exactly the correct size to clear these denominators. Obviously, we don't know what this E2 term looks like. We don't know what the stable homotopy groups of spheres look like beyond degree 100 at least. And so this is enormously complicated, but somehow it has exactly the right size so that this can happen. How this exactly happens is I don't know if we will ever know that. Okay, so now finally we should take cohomology, and again Chern and Siegen tells us that, so let's see, so we should take cohomology. So Chern and Siegen tell us, so we have now this Hochschild homology object with a circle action, and if we take homotopy groups, then we get a co-chain complex, and we could then take its cohomology. But Chern and Siegen tell us don't do that, form cohomology using the circle action directly. Okay, so what does that mean? It means the following. We take this to be the Tate spectrum of the circle acting on T. Let me explain what that means. So if I have let's see, if I have a space or spectrum with a G action, I can take the fixed points in the sense of higher algebra, which is written in this way. This functor does not preserve co-limits, but it admits a best approximation by one that does. So here's the best approximation by functor that preserves co-limits. And now the Tate spectrum is then the co-fiber of that, or mapping cone of this map. If G is a finite group or a compact Lie group, then we can say what this is. Then this is take x and shift x by the adjoint representation of G, and then take orbits of the action. And this map here is called the norm map. Okay. In any case, this is the higher algebra, analog of taking cohomology. So that's what Kohn and Secant tell us that we should do here. How do you now calculate the homotopy groups of this? So for that there's a spectral sequence which looks like this. It's an upper half-plane spectral sequence. So this is the Tate cohomology of the group T acting trivially on the homology groups and converging to the homotopy groups here. Oh, which I will write. Like this. Yeah. This is sorry. So this is called periodic cyclic homology. But you should think of that as being the analog of, or this is an extension of the Rham cohomology. Okay, so now I will explain what this looks like in the case of Fp over the sphere. So from now on, I will always consider the sphere as the ground ring, and so I will write THH of x for HH of x over the sphere, and TP of x for HP of x over the sphere. Maybe I can do that here. Okay, so now for x spec Fp, what does this look like? So this upper half-plane spectral sequence looks like this. So let me first draw this and then try to say something. Okay, so here we have 1. Here we have the Bökstedt generator x squared, and x cubed. So on this line we have the topological Rothschild homology of Fp, which was a polynomial algebra over Fp on this generator x. Then here we have the cohomology of the group T acting trivially on Fp. So this is the cohomology of Cp infinity. So here we have a generator T, which is the first Chern class of O of 1, and then we have T squared, T cubed, and so on. And that we take cohomology means that we also we similarly have the negative powers of T. Okay, so everything sits in even total degree, and therefore there are no differentials. So if we look in total degree 0, we have a ring equipped with a complete and separated descending filtration, such that all the filtration quotients are Fp. Now, if the circle action on HHH of Fp was trivial, then the projection onto the top graded piece would have a section, and this would just become a power series ring. So this is what topologists are used to in the case of a complex orientable spectrum. However, the fact that we have the circle action, this non-trivial circle action, makes this a much more interesting ring. Namely, here gets instead the ring of Witt vectors, which is the p-adic integers. So this element here, which is t times x, represents p times 1. So we have p here as p squared here, p cubed. Oops, p cubed and p to the fourth and so on. So the ring that we see here is the p-adic integers. More generally, in the case of a perfectoid ring, the ring that you get here is Fontaine's ring ANth of p-adic periods. So all of this it comes from the non-trivial circle action on HHH. Yeah. Okay. In particular, these TP groups of of Fp are too periodic, because if we look here in degree 2, we have, so the group in degree 2 is a module over the group in degree 1, but we see immediately here that it's a free module of rank 1 on a class that is represented by this. So therefore we see that, so for any x that is defined over Fp, these groups are too periodic. However, if x is not supported at a single prime, then this is no longer true, but not for x over c in general. So this cohomology theory so this is similar to the zeta function. If we are supported at a single prime, the zeta function is periodic, but if we have more primes, it's not. And so this cohomology theory has the same property. The most dramatic example of non-periodicity is if we take HHH of the sphere itself. In that case, we will here on the vertical lines have the stable homotopy groups of spheres, and now it's known that there's enough that everything in negative total degree, so everything below this line, is killed by differentials. Again, we obviously don't know what these differentials look like, but that's the way it is. Okay, so now to come to Dehninger's formalism, so I can now state the following theorem. So let x over Fp be smooth and proper. And let iota be a choice of embedding of the p-adic integers in the complex numbers. So this cohomology theory here, when we are over Fp, takes values in modules over the p-adic integers, but we would like to have a cohomology theory that takes values in complex numbers. We can do that by choosing such an embedding. Obviously, that is not what you would like to do, so this is not the end of the story. Then the zeta function can now be expressed as the regularized determinant of S times the identity minus an operator theta on the groups in odd degree extended up to Z divided by the regularized determinant of S times the identity, the same operator on the even part. Here. So this is a countably infinite dimensional complex vector space, and it has this operator, and there's a way to get a complex number called the regularized determinant out of that. There's no topology on this. This is not a Hilbert space, it's just that as an algebraic vector space. So what is this theta? So Dehninger tells us that we should have a Frobenius flow. So for every positive real number, we should have a Frobenius, a teeth Frobenius, and that should induce a map on this cohomology theory, and then we should take the derivative at t equal to 1, and that should be our theta. Now we don't have that, but we have a pth Frobenius, and so that should then be related to the map on this cohomology theory induced by the geometric Frobenius in this way. So this defines, so if we choose a branch of the pth logarithm, that defines theta, and now we have z worth of choices, but that's also how many groups we have, so we just use all the choices, and if you do that, then this formula is correct. Okay. Yeah. Okay. There's a very so there's a nice proof of this formula by which was pointed out by Tabuada, but it's based on work by Blomberg and Mendel, and in a better form by Antio, Matthew, and Nicolaus, using that TP tensor, or TP with P inverted, is a symmetric monoidal functor from stable infinity categories over Fp to graded Fp or graded C vector spaces. However, this is not, this proof uses the existence of the geometric Frobenius, and we would like to get away from that. So, because another consequence of descending from the natural numbers to the sphere, somewhat surprisingly, is that you get a Frobenius. So, the Frobenius is not a characteristic P phenomenon. The Frobenius is a higher algebra phenomenon, and we then only see it in algebra in characteristic P, but it's always there in higher algebra. So let me explain this. So this gives an internal Frobenius. So this was first discovered by Bökstedt-Hsiang-Madsen, and it's now much better understood in the work of Nicolaus and Scholze. So if X is a spectrum and P a prime number, then the Tate diagonal is a map from X to X tensored with itself P times over the sphere, and then the Tate construction of the cyclic group of order P acting on this P-fold tensor product. And this is induced by exactness of the source and target as functions of X from, so if we take the p-fold tensor product of the sphere, that's just the sphere again. So here the action is trivial, and so if we take fixed points, it receives a map, a canonical map from the sphere. And now there's always a map, as I explained over here, from homotopy, from fixed points to the Tate. Oops. Like that. Okay, so this gives this map. This is a map that does not exist in algebra. It only exists in higher algebra. It's responsible for the Steenert operations. For example, yeah, and I can say the reason that this exists here is precisely this fact that the stable infinity category of spectra is free as a presentable stable infinity category on a single generator S, and therefore if you know how to map in that case, you can build your way up to the general case from that, because there are no relations you have to check. Okay, so now if we have a commutative algebra in spectra, so let's see, so we have this map here. So THH of A was the unique was a universal example of an algebra with a circle action that receives an algebra map from A. In the same way, A to the tensor P is the universal example of an algebra with a CP action that receives a map from A. Since this has a circle action, it certainly has a CP action, so therefore by the universal example a property of this, we get a map here which is CP equivariant. So we can take the induced map on Tate spectra. But now here we have this Tate diagonal map, and therefore by the universal, so this is equivariant and this is equivariant, so by the universal property there exists a unique T equivariant map here that makes this diagram commute. So strictly speaking, the circle that acts here is T mod CP, but we can identify that here by sending Z to C to the 1 over PCP. Okay. So this is the additional structure that HHH has, that Hochschild homology over a general base does not, these internal Frobenius operators. So, yeah, this induces a map on. So since this is equivariant, we can take the induced map on fixed points. This here I will call negative cyclic homology. And Nicolaus and Scholze show that this is TP. So this is again the Tate spectrum, at least after completion at P. So this is Nicolaus and Scholze's Tate orbit lemma. This is an amazing fact which homotopy theory had missed, and which Scholze somehow discovered by knowing p-adic Hodge theory, and that this had to be true. So now we get an induced map here, which I will again call phi p. Maybe let me, okay, yeah. So now for x over fp smooth and proper, if so we have this map and here we also have the canonical map from homotopy fixed points to Tate. And in this case, that's an equivalence. So we get an induced endomorphism of TP with P inverted. So this, let's see. So this is similar to a Stuka. So Tp of x is some module, and which is globally defined, and then it has this automorphism, but only after we punch a hole in it. So that's how Stukas work too. So this punching holes is not something that homotopy theorists have been used to doing. So it took us a long time to learn this. Okay, so now I can say that the internal Frobenius and the geometric Frobenius are related by that the geometric Frobenius is p to the j times the internal Frobenius, where j is the Bhatt-Morrow-Scholze. Oops. Wait. Okay, so let me conclude with saying some words about what that is. So long time ago, a Chern Hirsebruch defined a filtration of topological K-theory, which gives rise to the Chern Hirsebruch spectral sequence. So it looks like this. And it was a big deal when they did it because it was the first time that spectral sequences had been obtained by filtering something that was not a chain complex, but a spectrum instead. Voevodsky generalized this to algebraic K-theory and to schemes smooth over a field, and then this is motivic cohomology. Here on this piece, the pth Adams operator acts as p to the j times the identity, so this motivic weight here records how the Adams operators act. Now, Bhatt-Morrow and Scholze in the same way define a filtration of Tp such that such that the following which looks like this, such that here on the jth piece, the geometric Frobenius, if you're in characteristic P, acts as P to the j times the internal Frobenius. This is also a big deal. This was part of the citation for Scholze's Fields medal, that this is a new cohomology theory, and this is what makes it possible now to have integral comparison theorems in p-adic Hodge theory. Yeah, so let me stop. Sorry, let me just, so so you can see, so we don't need the geometric Frobenius to formulate this theorem. So we can now ask, if we have a scheme over the p-adic integers or even over the integers, does such a representation hold? So for example, if you take the integers and you complete at p, then you get some groups which are now much worse, but they have the correct Frobenius eigenvalues. So the eigenvalues are the correct eigenvalues to give the the Euler factor at p of the Riemann zeta function. However, the operator does not act on a one-dimensional complex vector space as you would like, but instead on a countable product of copies of Cp. So we need to figure out what numbers really are so that we can connect these two. So let me stop there.
How do you account for the Archimedean Euler factor?
Yeah, that's also a good question. So so Conan Consani has given a similar formula for the Euler factor for the Archimedean Euler factors by using some. Yeah, let's see. Yeah, so to get the non-Archimedean Euler factors, you have like a Z-graded complex vector space with an operator. But to get the Archimedean Euler factors, it's like N-graded, so it's only graded. It's not periodic. It begins somewhere and then goes in one direction. So it's very important exactly where you begin. And so they define something they call Archimedean cyclic homology that accounts for this. However, they are cheating a bit because the cohomology theory that they define also has homology in negative degrees, and they just pretend they are not there. And but obviously there's an explanation missing for how, or there's something missing that can eliminate what you have in negative degrees. It's very interesting that the sphere has exactly this property that the Tate spectrum does not have homotopy groups in negative degrees. So perhaps the sphere knows Archimedean places too in some way.
More questions? If not, we should thank Lars for taking us from 20,000 years ago until more or less the present day. Thank you.